Yeah, speaking of math education, let's see what we can do here. Last time we were talking about geometric distribution, one of our 6 or 7 distributions. And so let's say some more about the geometric distribution. So we said when to use it. It's when we want to look at the following random variable. It's the number of trials to the first success, where the trials in question are Bernoulli trials. They're independent trials, all with the same success probability p. So that's when we want to apply it, and how to apply it. Well, we had these 3 equations last time. The probability mass function is given as follows: the probability that it takes that the first success occurs on the kth trial. One minus p to the k minus 1 for those first k minus 1 trials that all fail, times p for that success on the kth trial. The probability that w is strictly larger than k, well, that just means that the first k trials all failed. 1 minus p to the kth power. And so we get the cumulative distribution function. That's the complement of the event w larger than k. So its probability is 1 minus 1. Well, so last time we obtained these equations. One thing we didn't say is why it's called geometric. Where's the geometry? Well, let me remind you of something from algebra. The geometric series. You have the following infinite sum, where each term is r times the previous term. R, I guess, for ratio. Okay, this infinite sum, well, it converges if r is between minus 1 and 1. And the sum is 1 over 1 minus r. I forget just when this comes up in algebra, but here it is again. And the reason that's the sum, suppose you're stuck on this desert island and you're trying to remember the sum for the geometric series. Here's how you can get it. Call this sum S. So then r times s would be, well, 1 times r, that's r. And r squared. Well, it looks a lot like the previous line, except without the 1. And so if we subtract s minus r times s, it's just 1. All those other terms cancel. This factors. Yeah, even on a desert island, we can calculate the sum of this geometric series. Call this equation number 1. What if we take derivatives of both sides? We'll get another interesting equation. We'll call equation number 2. We get 0 plus 1 plus 2r. Better write this down. 1 plus r plus 2r plus 3r squared, and so forth and so on. Well, if the function of r on the left is the same as the function on the right, they have the same derivatives. And so the derivative of this, first time we've taken a derivative in this class, isn't it? Yeah, so the derivative of 1 over x is minus 1 over x squared. So we have the minus 1 minus r squared, and then the chain rule, the derivative of 1 minus r, which is minus 1. So that puts the sign back to being positive. Well, end of our excursion into algebra and related things. Back to the geometric distribution. Let's verify computationally that these probabilities add up to 1. It'll be a good warm-up for the next problem. So we want to take, for the geometric distribution, the probability that W is 1 plus the probability that it's 2 and so forth. The smallest it can be is 1. These had better add up to 1. Yeah, did you have a question?
I don't understand what the odds are.
Where, the question about where the R? Which R? Oh. Yeah, good. Where did, the question is, where did that R come from? It came from a mistake. Yes. It's not there. You never saw it. 0 plus 1 plus 2r plus 3r squared. Much better. Thank you. Okay, back to calculating this sum. So we want the probability that W is 1, that it succeeds on the very first. Right? So that formula there says the probability of that W is 1 is this. Of course, something raised to the 0th power is just 1. So we didn't even need to write that down. Plus the probability that W is 2. Plug in k equals 2 there. We plug in k equals 3. And we have this infinite sum, but each term has that power, has that factor of p in it. Let's factor that out. One plus 1. Aha, nothing but a geometric series where r is 1 minus p. So we'll apply equation number 1 with r is 1 minus p. to this sum to the series in brackets there. So by equation number 1 says that's 1 over 1 minus r, and r here is 1 minus p. Okay, 1 minus p simplifies a bunch. It's just p. Ah, good. It added up to 1. Now for the next problem, we want to calculate the expected value of W, where W has the geometric distribution. Okay, so this is something we'll need to know. We know what the range of W, it can be 1 or 2 or 3, so we need to take this weighted sum, but it's now an infinite sum. So we take 1 times the probability that it's 1, plus 2 times the probability that it's 2, and so forth and so on, this infinite sum. And the probability that it's 1, as over there, is just p times something to the 0th power. The probability that it's 2, that's 1 minus p times p. The probability that it's 3, and we want this sum. Well, again, we can factor out that common factor of p and see what we have left. Well, there's a 1 there. 2 times 1 minus p plus 3 times so the next term would be 4 times 1 minus p cubed, and so forth. So that term in brackets is exactly what we have in equation number 2 here. Good. So we can apply equation number 2, where again r is 1 minus p, to that series in the brackets there, and it says the sum we get, 1 over 1 minus p that thing squared, and again 1 minus p is just p. There's the answer. The expected value is 1 over p. This gives us the mean for the geometric distribution. So what that is telling us is, for example, if p is 1 over 100, the expected number of trials to get the first success is 100 trials. If p is 1/10, well, you expect on the average it's going to take 10 trials to get that first success. And we also want the variance. And I'll just cheat. Okay, a similar calculation. Okay, but you have to use the second derivative. Right? We use the first derivative to get equation number 2, and so take derivatives again to get an equation number 3. And a bunch of algebra gives the variance. One minus p over p squared. So the standard deviation comes from knowing the variance. So the geometric distribution has this standard deviation. Well, knowing that, let's work the following problem. Suppose we have the geometric distribution where the parameter p is, say, 1/10. What's the probability that when we run the experiment, we get a value for w that's within one standard deviation of the mean? Now let me write that down. That's the geometric distribution. And we want to find the probability within one standard deviation of the mean. A problem we've done before in other situations. So let's see what we get here. First of all, what is the mean? Well, so we have a formula for the mean. It's 1 over 0.1. Yeah, the mean is 10. We expect 10 trials to get our first success. And the standard deviation, well, the variance uh, 1 minus p, 0.9, over 0.1 squared. Okay, so that's 0.9 divided by 1 over 100, so 0.9 times 100. That's 90. So the standard deviation is the square root of 90. Well, we can think of that as 9 times 10, because 9 is a perfect square. It's 3 times the square root of 10. Square root of 10 is around, well, it's close to pi, actually. This is a little more than 9, but it's less than 10. It's about 9.5. 9.487 would be closer. It's the standard deviation. Yeah, the mean is only 10. Looks like kind of a big standard deviation. Well, that's because, you know, W could be 1,000,000. Yeah, with small probability, but those big numbers pull the standard deviation up. So what we want is the probability that the distance between W and the mean is no more than 9.5. There's the probability that W is at least 10 minus 1 standard deviation, and at most 10 plus 1 standard deviation. Well, of course, W can only be a whole number. So this simplifies. First, let's do the arithmetic. This says W is between 1/2 and 19.5. Yeah, but W is always at least 1/2. We can ignore that. That's always true. And the only way it can be less than 19.5 is to be 19 or less, because it's got to be a whole number. So we want the cumulative distribution at 19. Okay, and we have a formula for that up at the upper board. There's a formula for it somewhere. I guess it's been erased. For the cumulative distribution, it's 1 minus p. We want to say it's not the case that we have these 19 straight failures. P is 1/10, so 1 minus p is 0.9. And then we ask our calculator what this is. It's about 86.5%. It's a larger number than we got for the same question on the binomial distribution with the numbers we used. It's because the geometric distribution has a comparatively large standard deviation. Now, let's change the game a little. Let's look at a different random variable, W sub 2. That's the number of trials to get 2 successes, number of trials to get the second success. Well, we figure it's going to take more trials to get 2 successes. For one thing, the smallest W2 could possibly be is 2. To get 2 successes, you're going to need at least 2 trials, or it could be 3 or 4. It is even imaginable that you never get a second success, although that has probability 0. Well, a new random variable, we can ask the same questions. What's the probability mass function? Or for starters, what's the probability that the next time we run the experiment, W2 is 5? Right, that's one of the things that might be. How likely? Well, let's calculate this probability. Okay, in terms of whatever the success probability P happens to be, we're not given a number for P. So the answer will involve what the success probability is for. Well, so we need to look at this event, W2 equals 5. How can that happen? Well, that means in the first 4 trials, here we imagine the first 4 trials. We had exactly 1 success. If the second one was on the 5th trial, that means the first 4 had 1 success and 3 failures. And then the 5th trial, that had a success. So here's a picture, if you like, of the event W2 equals 5. And how likely is this? Well, we know how to do this problem from the binomial distribution. The probability of 1 success in 4 trials, well, we write that down. Four choose 1. P to the power 1 for the 1 success. 1 minus P to the n minus k, so that's 3, for those 3 failures. And then we want the 5th trial to be a success. Probability P. Trials are independent, so we multiply. 4 choose 1 is just 4. Yeah, the probability that W2 is 5 is given by this expression. Well, now we're ready to do the real problem. What's the probability that W2 is k? That is, we want to find the probability mass function for W2. So that was just a warm-up. Here's the real problem. So the answer will involve P and K, and we want an algebraic expression for the probability mass function. But exactly the same method. Let's look at this event, W2 equals K, and see how that could happen. Well, means that in the first K minus 1 trials, we had exactly 1 success. No more, no less. And then finally, the kth trial had a success, which was the second success. So for the second success to be on the kth trial, it's got to go like this. And we know the probabilities. The binomial distribution, we know how to find the probability of exactly 1 success in k minus 1 trials. K minus 1 choose 1. P to the power 1 for that 1 success. 1 minus P to the k minus 2. K minus 1 trials and then one was a success, k minus 2 of them failed. So that's the probability for that much. And the probability of that one success is just p. And they're independent. We multiply. K minus 1 times p squared, 1 minus p to the k minus 2. Well, as a check, what if k is 5? Then it should agree with what we got before. Well, if k is 5, k minus 1, that's 4. K minus 2 is 3. What luck. Which brings us to a homework problem, one of today's problems. Which is the same thing for W3. W3 is a number of trials to get 3 successes. Well, I don't want to spoil the fun because you're going to do this, but I recommend doing it by the same method. How could you get the 3rd trial on the kth success? The 3rd success on the kth trial. Yeah, we can draw a picture of that event and calculate its probability. Well, back to calculating the waiting time for the first success. But where we don't exactly have Bernoulli trials, rather it's more an ongoing thing. The first success. Well, I'm going to use this phrase, continuous trials. That is, they're going on all the time. For example, let's assume that Los Angeles gets a disastrous earthquake on the average once every century. Once a century. On the average. Okay, you look at the last 1,000,000 years and we decide that it's about once a century. Get an earthquake, I don't know, maybe 7.0 or something, which would be a disaster. The Northridge earthquake, for comparison, was 6.7, and that extra 0.3 makes a big difference. Well, we're interested in what's going to happen in the next 10 years. Well, we don't know for sure, but what's the probability? Of one of these disasters. Well, we'll do this later, but there's warm-ups. What's pretty close is to think of this in terms of the binomial distribution. We have these we could think of each year as a trial. With success probability of 1 over 100, because a few of these earthquakes hit on the long-term average once a century. There's no particular pattern to the earthquakes. One year is as likely as another. But from what we're told, it's reasonable to think that each year might be that year of about 1 chance in 100. And we're looking at 10 trials, right? The next 10 years. And we could calculate the probability that there's at least one earthquake. Well, the probability of no earthquake so if we can define success as having a disastrous earthquake, the probability that that doesn't happen, 0 successes. Well, it's 10 choose 0, p to the 0, 1 minus p to the 10th, or in other words, 0.99 to the 10th. Which I didn't work out. We want the complement of that. I did work that out. Yeah, it's close to 1/10, as which one might guess. 10 years, probability 1 over 100. But there's nothing in the problem that says to use years. We could use a shorter time interval, like days. Well, let's do that and compare the numbers. Well, now we're looking at a whole bunch of trials in 10 years. Well, because of leap years, that last figure should really be more like 2 or 3. But about this number of days. And each day has a pretty small probability of success, that is, probability of a disastrous earthquake, about 1 over 36,524 or so for leap years. And if we work in days, the probability of 0 successes, that is, no earthquake in these 3,000 and some odd days, (1 minus p to the 3 power, where p p is this. And we get about the same number. About the same number. Which I did not work out. A tiny bit smaller than this. Here's our plan. We're going to take a limit as n goes to infinity. That is, instead of working in years, or days, or minutes, or seconds, we'll think of this as, well, I want to use the phrase continuous trials. It's just something ongoing. And the earthquake could hit at any instant. We got through that last second, okay. Keeping n times p at 1 over 100. I mean, here n times p was, 1 over 10. And here, n times p is 1 over 10. We're looking at this 1/10 of a century. So we'll do that. And we'll find that the probability of no earthquakes at all is e to the minus 1 over 10. The n times p here. That's the probability of no earthquake in this period. So the probability of that S is different from 0, that there is some earthquake, would be 1 minus this. Not very different from what we got from years. Okay, but it's a more natural interpretation of things like earthquakes or events where there's no particular unit of time involved. We just have this spread out. Well, time is continuous. It goes along. And a hit could occur at any moment, but we have some long-term rate. Well, so we take a limit. You remember about limits. And the exponential function, e to the x, comes up. Well, you remember about the exponential function, or if not, you're about to get reminded on Wednesday things about the exponential function. And then we can use this to calculate some probabilities. Well, got to stop for today.